Yes, so like Carsten mentioned, this is actually going to be a three-part presentation on synthetic data. So I'm going to speak first and talk about the high-level, strategy and research goals uh, of this area within the project. So mostly covering myself and Praveen's work. I'm then going to hand it over to Roberto and then followed by Matthew. Okay. So what I'm going to be talking about is first the role of synthetic data in ID systems. Uh, After that, a bit more of a detailed introduction into synthetic data generation. What are the different taxonomies, metrics, and trade-offs? The concept of differential privacy. Uh, what are its promises, limitations, and the different approaches that we can have? And finally, I'm going to end with a discussion on the algorithmic bias in biometric recognition systems and why we need controllable SDGs. All right. Okay. So yeah, I think this is going to be easy to motivate, but however, some of the key, uh, I would say, reasons why a publicly available data set is going to, benefit research into ID systems are primarily because it can help with the development and benchmarking of tools that are quite prevalent out there, which are used for biometric recognition. But we'll see later why whatever data that we have, which is being currently used for the development, may not be good enough. Secondly, there are a number of academic research out there, as well as a wide consensus even in the industry that a lot of these algorithms have some sort of a bias, which is making it unfair for certain sections of the population. And then beyond that, you can even use these. We do need a lot of data for developing tools that can detect fraud, as well as fake biometrics that are key to keeping the systems secure. And also smaller or not really small, but other use cases not really going to be covered in this presentation, but data is also required for modeling threats to these systems, as well as general purpose software testing use cases. Okay, so we need a lot of data, and we need it for all of these different reasons. But however, if as being part of this research team now for almost 3 years now, I've never seen one single observation of real data from an ID system till now, right? So what can we do? So synthetic data seems like the most obvious and reliable approach in this scenario. So the idea is to release a data set that has the same statistical properties as any real world data from an ID system would have. This can help us also simulate situations that have not been encountered yet or captured by real data. Synthetic data can also help with anticipating attacks and threats, and therefore design ID systems in a better way to mitigate these threats. So, okay, we do want to now generate synthetic data for all parts of the ID system. So let's just look at what are the different kinds of data that reside within an ID system. So taking MOSIP as an example, MOSIP likes to differentiate between data that is categorized as part of the ID lifecycle management and ID authentication as two separate categories. In ID lifecycle management, these are more, you can think of them as static data. So so this captures all your data that is collected during your registration phase, for example, like your tabular data that includes your demographic information and other sorts of biometric information, including fingerprints, iris, face, and even voices, which is going to be rolled out in the future. Now, this is quite different from the data that is captured in the authentication phase. So for example, the bread and butter data that is collected in an ID system are authentication requests. So this is form of a time series data. So here, there are a number of interesting use cases here for example, detecting fraud or any kind of anomalous transactions or authentications. You also have authentication requests coming in, which are going to be, authenticated or verified using newly collected images or audio biometric information, which are then going to be compared with your, the biometrics collected during registration. So overall, I would say there are, from a purely data perspective, I would say there are two kinds of data. There is tabular data and there is non-tabular data, so which are basically the biometric information. So we want to generate all these kinds of data, right? So let's see what are the key considerations we need to have while generating synthetic data for ID systems. So this is a very nice slide, which I have stolen from Mirko, who presented earlier today, and just made a couple of modifications to it. So he has done a lot of work looking at privacy, preserving synthetic data, and what kind of metrics can be used to evaluate such data. So what are the key qualities that a synthetic data set should have, right? So it should have syntactical accuracy at a minimum, right? So that's something really non-negotiable. It should have, it should preserve privacy. It should not be leaking out individual confidential information. It should be unbiased, which we are going to talk about a little more later. And of course, statistical accuracy and efficiency, right? It should be representative of real world information, and the data generation method should also be efficient. It should happen in a reasonable amount of time. And there are a number of other metrics and trade-offs that are there in the process of generating synthetic data. So for example, one of the popular ones is the fact that privacy versus fidelity, right? So if you want to generate synthetic data that is very private, then you are going to inevitably lose some of the accuracy that you want to preserve in terms of the properties of the data. All right, so now let's look at more of the conceptual side of things. So when we do want to generate synthetic data, we rely on generative models. So how does a typical generative model work? It works by building a joint distribution of all the different data variables by training on some small set of real data. I mean, it need not be small, but typically that might be how it works in practice. Now, once the joint distribution is learned, any amount of synthetic data can be obtained by simply sampling from this learned distribution. And what these models are trying to do when they're learning in the learning phase is that they're trying to preserve as many statistical properties of the real data set that it has access to. However, all generative models are not privacy preserving by default, right? So this is where the key concept of differential privacy comes in. So differential privacy is, enables us to share information about a data set while ensuring that, any individual level information is not exposed. So, I mean, in other words, how you can think of this is that, let's say you have two copies of real data, and in one of the copies, you remove all observations corresponding to a single individual. What differential privacy guarantees is that the synthetic data generated from either of those copies are going to be almost indistinguishable, right? So the absence or presence of any particular individual in the data set is not going to affect the data that you generate. So I'm not going to go into the math behind it, but a couple of other points to understand about differential privacy is that so when we talk about preserving properties, in this particular case, we are typically talking about marginal distributions and correlations between the various features in the data. And however, like we spoke about the trade-off before, one of the key trade-offs that differential privacy kind of brings to the table is the trade-off between utility and privacy. And therefore, there is an inherent limit if you go down this DP-enabled approach, which might be, something that's absolutely fine and maybe necessary. So finally, concluding the section on DP algorithms. So fundamentally, there are two different types of DP algorithms. So one is the marginal based approach. These are the ones that are typically employed when we are dealing with tabular data. So there are a number of approaches here, and the core idea here is that you preserve the marginal distributions, most likely like the low dimensional, maybe 2 or 3 dimensional marginal distributions of the variables in the data. And you learn that from the real data, you add some noise to it, and then you reconstruct data, which is what you are left with as the synthetic data. Of course, you also have deep learning based methods, which can be used for both tabular data as well as, image or voice data, which my colleagues are going to talk about in more detail later. In general, deep learning based methods have been reported to have less accuracy than marginal based methods, but when your data is high dimensional, these are the ones you might end up using most of the time. Okay, now something that is quite of a keen interest for me, as well as a few others in the team, is what do we do about the algorithmic bias that we have in these algorithms? So here I'm, the title of the slide is biometric recognition, but, I'm going to take an example of face recognition to talk about the different aspects of facial images that are sources of bias, right? So these may be due to variations that exist, between different groups of people, defined by their race or sex, for example. It may also be due to, like, a person may be misidentified because they have changed their hairstyle or hair color even, right? So these are all possible sources of misidentification. Issues can also arise when the image that you are capturing during the authentication or identification is, of a different specification, either due to the lighting or the resolution, or maybe even things like the pose of the image. And finally, these biases that these algorithms can have also change as these systems scale, right? So as there are more and more, let's say, there are individuals in the order of millions or even billions in your data, then it is natural to expect that your chance of being misidentified with somebody else is even higher, right? So we need to be able to kind of test our methods in a complete way against all of these different sources of bias. And this is where we feel synthetic data has a massive role to play, because such kind of experiments that can provide us insight into all these different variations and effects of scale, etc., is simply not possible in most real data sets. Yeah, so like I mentioned, we need to kind of understand the impact of these different sources of bias. And typically, most of these algorithms that are used in real time end up having a bias across these different variations because they were trained on imbalanced data sets, right? One of the typical, or one of the most common examples of this is with skin tone. For example, it is well published that people of darker skin tones, especially females of darker skin tones, have the highest probability of being misidentified as compared to any other race or sex group in the population. So we need to of course overcome this by creating balanced data sets that can then be used to train all our models on. So how do we do that? So how do we generate data that have specific attributes? So this is not a trivial. So there are a number of ways we can try to do this, and we are within the team trying to explore all of these following options. So one method to do this would be conditional generation. So I mean, in the AI space, I think conditional generation is very popular. We have a number of methods that are coming up that are, you might have seen your typical text to image generation models out there. But one of the key limitations here is that it's not really scalable when the number of features you might want to balance your data set against is a very high number. Okay. So among these three approaches, the one that we really like, which is also scalable, is latent code manipulation. So what that means is that any image or voice or any biometric for that matter, how they are fundamentally processed in these algorithms is that we get a high dimensional numerical representation of each image or fingerprint or voice. And what we can then do is that we can manipulate these latent representations to get the variations that we want, right? So, but for that, what we need to understand is that in what direction we need to travel in this latent space to get our desired change. So this is one of the things that I've been personally focusing on right now. And I think Roberto will also be speaking about some of the experiments that he has done in this area shortly after this. And of course, finally, one of the simplest things you could potentially do is that you can just start building or training synthetic data generators for each specific variation that you want, right? So maybe just build one model per variation that you want. But again, this is going to suffer from scalability issues and maybe even other properties of just the domain of image generation that you might miss on, right? Maybe there are learnings from certain other variations that you could use to generate more accurate images, which would not be possible if you went down this route. So I hope this gave a decent kind of overview into the role that synthetic data can play in the design and development of ID systems. I think it's important that we understand what are the metrics we need to be measuring or evaluating the synthetic data generators against, depending on what application we want to use it for. Synthetic data are not private by default. So the concept of differential privacy should be seriously considered. And there are a lot of methods that are being developed and already published that do guarantee differential privacy for synthetic data. And finally, when we do want to kind of curate a balanced data set so that we can build fairer models, we need to figure out a way we can use these synthetic data generators in a controllable manner, right? So these are the kind of the key highlights. Roberto will speak right now specifically with respect to facial images and the work he has done there, both in generating synthetic faces as well as detecting fakes